Hello, chemistry students. Here are your Chapter 13 notes for Day 4. We will be starting at electron configuration on your outline and going through frequency. To start, again, I want to kind of review how we use that periodic table to know the order in which we fill orbitals. So remember that these periods over here, these are our energy levels. And I kind of like to have them over on the other side as well. Okay. Then we really can kind of put helium over here, but this first row, remember, this is our S sublevel. And that's going to be equal to our period number. These over here, with the exception of helium, this is our P sublevel. So remember, that means we're putting electrons into our 3p orbital. And because there are 3 p's, that's why there's 6 columns here. Down here, these are our D sublevel. And remember, the D sublevels are one behind, right? So there are period number -1. So although these scandium through zinc are in the 4th period, those are 3Ds. Remember that lanthanum and actinium really belong right here. These are our F sublevel. And remember, these are 2 behind our period. Oops. But if you read your periodic table like a table or like a newspaper from the upper left to the lower right, it gives you the order that you're filling these electrons in. So you don't have to memorize some list. You can just use your periodic table. So my preference today, as we start to talk about electron configuration, is that you have your periodic table out and handy and are using it in that way. So when we were doing the orbital notations yesterday, they take up a lot of space, right? To do that bismuth one, it took up most of a page of my iPad here, okay? So that's kind of annoying and a little bit time consuming. So when we talk about doing an electron configuration, this really is sort of a shorthand notation. So it's going to be shorter, okay, than those orbital notations. In an electron configuration, you're writing the energy level, and the symbol of every sublevel occupied by an electron. So instead of using the either boxes, which I don't really do, but the lines, you're not going to have lines here. Okay, you're just going to have like those labels that were underneath them. You indicate the number of electrons occupying each sublevel with a superscript And superscripts are those numbers that are up high, so like X to the second, that second is a superscript. The sum of the superscripts equals the number of electrons in the atom. So your superscripts represent electrons in this formation, or in this notation. So, for example, we're going to start with hydrogen, which, again, we look at hydrogen's atomic number, and hydrogen's atomic number is 1, so it has 1 electron. Our first energy level, right here, this is our first S, so that's going to be 1s, and it has 1 electron, so it's 1s1. So that is the electron configuration for hydrogen. Let's look at helium, which has 2 electrons because its atomic number is 2. We're still in the first main energy level, we're still in our S sublevel, and it can only hold 2 electrons, so it's 1s2, which is 2 electrons like we're supposed to have. For lithium, which is atomic number 3, so it has 3 electrons. Again, I'm going to still start at my top left, so that's my 1s, and I'm going to have 2 electrons in it, which takes me to helium. And then my next energy level I come to is my second, and my S sublevel, and it will only have 1 electron to give me a total of 3 electrons. For carbon, which has atomic number 6, so it has 6 electrons. Again, I'm starting out with my 1s. I have to completely fill it with the 2 electrons before I move on to my 2s, which I have to completely fill with the 2 electrons it can hold. Next, I come to my 2p's, and I have 4 electrons so far, so I'm going to have 2 electrons in my 2p. 2 plus 2 plus 2 gives me 6 electrons total. For nitrogen, which has 7 electrons because its atomic number is 7, I'm still starting at my first energy level, my S sublevel, and the fact that it can hold 2 electrons. Next, I come to my second energy level, my S sublevel, and the fact that it can hold 2 electrons. Next, I come to my 2, still my second energy level, but my P sublevel, and 2, 4, so there will be 3 electrons there to total 7. Oxygen, which is atomic number 8, so it has 8 electrons. Again, I'm going to start at my first energy level, my S sublevel, and put 2 electrons. Next, I come to my second energy level, first the S sublevel, it's going to be completely full with its 2 electrons. Next, I come to my 2p. Remember, my 2p can hold 6 electrons total because there are 3 2p's. So I'm at 2, 4. So I need 6, I'm at 4, I need 4 more, so this is going to be 2p4. So there's my electron configuration for oxygen. For fluorine, atomic number 9, so it has 9 electrons. Again, I'm going to start with my 1s, completely full with 2 electrons. Next, I come to my 2s, completely full with 2 electrons. Next, I come to my 2p, which can hold 6. I have 4. I need 5 more, so it's 2p5. Neon, atomic number 10, so it has 10 electrons. Again, first energy level, S sublevel, completely full with its 2 electrons. Second energy level, S sublevel, completely full with its 2 electrons. Next, I come to my 2p. It can hold up to 6. I have 4. I need 6. So my electron configuration for neon is 1s2, 2s2, 2p6. For sodium, which has 11 electrons, so it is going to be 1s2, 2s2, I'm at 4, come to my 2p, it can only hold 6, So that's going to take me to 10. So now I come to my next energy level, which is my third, my S sublevel, and I'm going to have 1 electron in there. So go ahead and do polonium. So again, pause the video, see if you can do polonium on your own, and when you're finished doing it, you can unpause the video and see if what you've done matches what I do. So polonium is atomic number 84, which means it has 84 electrons. So 1s2, 2s2 comes next. Then I have my 2p. It's going to be completely full. 3s, completely full. After 3, completely full, which means 2, not 1. Okay. Next I come to my 3p, which will be completely full with 6. That takes me to argon. So next I come to 4s with 2, which takes me to calcium. Next I come to my Ds, but remember my Ds are 1 behind, so if I'm in the 4th period, these are going to be 3 Ds, and they can hold 10 electrons total, which takes me to zinc. Next I come to my 4Ps, and again 6, which takes me to krypton. Next I come to my 5s, 2, which takes me to strontium, 4d10, which takes me to cadmium, 5p6, which takes me to xenon. So I'm getting close, right? I just have 1 row left to go. So next I come to my 6s and 2, which takes me to barium. Now be careful, right? Atomic number wise, next I come to that top row that's pulled out and underneath the periodic table, which are my Fs, and they're 4 behind, or 2 behind. So if I'm in the 6th energy level, they are 4 Fs, and there are 14. And then I come to my 5 Ds, and there are 10. So that's going to take me to mercury. So I'm getting close to polonium. So now I have my I'm in my 6th energy level, so it's 6p, and then to figure out how many electrons, I can actually just count over. So thallium's 1, lead is 2, bismuth is 3, polonium is 4, so 4p4. And to check this, I would add up the superscripts of all of these and see that it equals 84. Now, this is still fairly tedious. So there is kind of even a shorter way to do this, okay? So for example, if I look back to my oxygen, you can place in kind of square brackets the name, I don't want to say name, I want to say the symbol of the noble gas, which remember is my group 18, and then add the electron configuration after that. So what would this look like for oxygen? So for oxygen, this isn't in that highest energy occupied energy level. So for oxygen, if I go up a row and to the right, the noble gas is helium. So I'm going to put helium. And what this means is the noble gas, or the electron configuration of helium, which is this 1s2. And then I just write 2s2, 2p4. So what would that look like for neon? It still would be helium because that's the noble gas of the row above it. And then 2s2, 2p6. For sodium, sodium's in the third row, so I'm going to go to the second row and to the noble gas, which is neon this time. And again, that means the electron configuration of neon, which is this part of it, and then 3s1. So for palladium, though, for sure that's pretty nice, right? Because I'm in the 6th main energy level. So for palladium, I go up a row into the end and I have xenon. Now, the part of this configuration that is xenon is all the way through here. All of this is xenon's electron configuration. So I can avoid writing all of that and just write 6s2, 4f14, 5d10, 6p4. So that certainly is a lot less writing. So by putting that noble gas in those square brackets, you're saying the electron configuration of that noble gas and then this other stuff. So you're welcome to do it whichever way you prefer. So how do we use the periodic table to know the order of orbital filling? That's what we've been doing, okay? So again, we just have to kind of remember that the elements on the periodic table are filling their orbitals with the lowest energy first. So we just have to be able to recognize that S block where we're putting electrons into our S sublevel, our P block where we're putting electrons into our P sublevel, our D block where we're putting electrons into our D sublevel, and our F block where we're putting electrons into our F sublevel. And in our S block, right, there are 2 elements because an S block will hold 2 electrons. In our F block, there are 6 elements because F orbitals will hold total, there's 3 of them each holding 2, they'll hold 6 electrons. In our D block, there are 10 elements because there are 10 or 5 orbitals each holding 2 electrons, so 10 electrons. And in our F block, there are 14 elements because there are 7 F orbitals each holding 2 electrons, so 14. Okay? So we've been practicing this. We do need to remember that our D block is 1 behind our period number that we're in, and our F block is 2 behind the period that we're in. So, again, a couple more practices here. Oh, look, I've got practice there. So, practice. Write the electron configuration of boron. Do the electron configuration of silicon. And then for those, I want you to answer how many unpaired electrons does each atom have? Okay, so again, go ahead and pause your video and do these. And when you are finished doing them, then go ahead and unpause the video and check your work. So for boron, which has an atomic number of 5, so it has 5 electrons, I'm going to be 1s2, that's what I come to first. Then I come to my 2s, 2, and then I come to my 2p, and I'm going to have 1. Or, okay, remember I could put my helium in my square brackets, and then just say 2s2, 2p1. Either way would be fine. When I'm talking about silicon, again, I start up at my top left-hand corner, and I come to my 1s with 2 electrons, my 2s with 2 electrons, my 2p with 6 electrons, because silicon is in the 3rd period, 3s, 2 electrons, 3p, and I can kind of count over. Silicon's the second one, so it's going to be 3p2. Silicon should have 14 electrons. So 2, 4, plus 6 is 10, 12, 14 electrons. Or I can put my neon in my square bracket and then say 3s2, 3p2. Either way would be fine. The question about how many unpaired electrons does each atom have? Well, for boron, it has 1 unpaired electron, because that electron in the p orbital here is all by itself. Now with silicon, that looks a little bit tricky, because it looks like there might not be any, but remember, according to Hund's rule, I have to put 1 electron into each p orbital before I start to double up. So silicon actually has 2 unpaired electrons, okay, in that 2p, because there really would be a 2p, right, with 3 lines, and there'd be 1 electron in each, so that's 2 unpaired electrons. So hopefully you did all right answering those questions. All right, so there are some exceptional electron configurations where it doesn't exactly follow what we've been doing. With these, you need to know that a filled energy sublevels are more stable than partially filled sublevels. So because of that, sub-actual electron configurations differ from what we would predict, because although half-filled sublevels are not as stable as filled sublevels, they are more stable than other configurations. This mostly happens among the D and S sublevels because they are very similar in energy. So remember when we looked at this, right? Through here we come to our 4S and then our 3D. Well, it turns out that the 3Ds don't have very much more energy. It's just a tiny amount more energy. Okay? So, because that happens in this whole area of our periodic table, okay, they often kind of do some things that perhaps you wouldn't predict. So, to look at an example of this, we're going to look at copper, what we predict. So first I just want to do copper's prediction, and I'm going to go ahead and do that one where I put the noble gas in the square brackets. So I find copper on my periodic table, it's atomic number 29. So I go up a row and to the right, which is argon. So I'm going to put argon in my square bracket. And then I'm going to build from argon. So next I come to my 4s with 2 electrons. And then I come to my 3ds. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I just counted, starting at scandium to over to copper to figure out how many electrons that would be. So that's what I would predict. Now notice here, in this scenario, I have 2 electrons that are happy. Maybe I'll do it this way. And 9 electrons that are kind of unhappy because they're not completely full yet. So although that's what we predict, here's what copper actually is. It's argon, 4s1, 3d10. I still have the same number of electrons, 11, okay, in our outer shell or outer electron, outer energy level. But now I have 10 electrons that are happy because they're completely full and only 1 that's unhappy. And so that is a more stable electron configuration. Who else is going to do this? Every element in the same group or family as copper. So silver is going to do this, and gold are both going to also do this same thing with their electron configurations. Another example, okay, we want to look at chromium, what we predict. So for chromium, again, it's argon, and then it's 4s2, 3d, 1, 2, 3, 4. Okay, so again, right now I have two electrons that are happy and 4 that are kind of unhappy because they're not even half full here. So what does chromium actually do? It's argon, 4s1, 3d5. Why is this more stable? Because here now my S sublevel is half full, as is my D. And this is actually lower in energy than what we would normally predict for chromium. Who else is going to do this on the periodic table? Again, all the elements in the same group or family as chromium. So chromium, molybdenum, tungsten, and seaborgium are all going to have this kind of different electron configuration. So, continuing, we're going to talk about physics and the quantum mechanical model. We're going to talk about light and atomic spectra. We're going to start by talking about Isaac Newton, who lived from 1642 to 1727. And Isaac Newton, way back then, okay, tried to explain what was known about the behavior of light by assuming that light consists of or is made of particles. So he kind of said, like, if you don't see light, it's because there aren't light particles reaching your eye. When you do see light, it's because light particles have reached your eye. Okay, so Newton thought that light was made of particles. However, by 1900, there was enough experimental evidence to convince scientists that light consists or is made of waves. And in fact, scientists know that light consists or is made of electromagnetic waves. So, electromagnetic waves means we're talking about electromagnetic radiation. Now, you hear radiation and you think something bad, something dangerous. But electromagnetic radiation includes radio waves, microwaves, infrared waves, which are the red light bulbs that are used in fast food restaurants to keep things warm. Also used, we used them on the farm with our baby animals. When it was cold outside, we'd put a heat lamp, which was an infrared lamp, in their pen to help keep the babies warm. Invisible light. So our visible light, ultraviolet waves, X-rays, and gamma rays. So, yes, some forms of electromagnetic radiation are dangerous, right? Ultraviolet rays, you know that UV, that's why you put on sunscreen when you're outside in the sun, because UV rays can burn your skin and eventually cause skin cancer. You know, X-rays are dangerous because they give you something to protect yourself when you're going to have an X-ray taken. And gamma rays, that's our ozone layer and our atmosphere of our Earth that protects us from the gamma rays from outer space. All electromagnetic radiation, so all of these travel in a vacuum, not like a vacuum cleaner, just a space with no particles, at a speed of 2.998 times 10 to the 8th meters per second. So you do need to know the electromagnetic radiation, like Oh, we'll talk about it in a couple minutes because there's not really enough space. So you do need to know kind of how these go in order, but we'll talk about that after we've talked about frequency and wavelength. So right now, electromagnetic radiation, all of them travel in a vacuum. So these all travel at exactly the same speed at 2.998 times 10 to the 8th meters per second. So remember, that is pretty fast. But remember, for light to reach from the sun to the earth, remember that's 8 minutes. So even though that light is moving at 2.998 times 10 to the 8th meters per second in outer space, it still takes 8 minutes for that light to reach us here on Earth. So when we draw a wave, actually I'm going to kind of put it more in the middle, sorry. We draw a wave kind of looking like this. Okay. This line here, this is our 0 line. Okay. And we have some parts of this. Hopefully, perhaps you've learned some of these names, right? These high points are called a crest. So the way I've drawn this is I have 3 crests in my picture. These low points are called a trough. And again, the way I've drawn this, I have 3 troughs in my picture. And kind of when we describe this, we say that each complete wave cycle starts at 0, on the y-axis, increases to its highest value, passes through that 0 again to reach its lowest value and returns to 0 again. So every wave cycle starts at 0. So here's my starting point on the y-axis. Increases to its highest point, passes back through 0 to reach its lowest value, and returns to 0 again. So that is a complete wave cycle. So on this one, I actually have 3, right, wave cycles drawn. So with these waves, there are some labels. One of the labels is that we can talk about its amplitude. So this is the amplitude. Amplitude is defined as the wave's height from 0 to the crest, or the highest point. So again, that's our amplitude. Next, we're going to talk about the wavelength. The wavelength is the distance between crests. So this is our wavelength. So wavelength is the distance between the crests. And this is the Greek letter lambda. Lambda, I think that's how you spell it. It's a Greek letter, okay? It's used to kind of abbreviate wavelength. Frequency is defined as the number of wave cycles to pass a given point per unit of time. So to kind of imagine what frequency is, imagine you're standing on the end of a dock, and there's it's a wavy day out on the lake. And so to measure frequency, you would say for a minute, you would count how many crests of the wave go by the end of the dock in that minute. Okay? Now, in science, we're not usually going to talk about minutes. Okay? So the measurement of this is usually in cycles per second. So in science, we're going to talk about it in seconds. But if you were trying to count waves going by on a dock, you'd probably choose to use minutes. The SI unit, SI stands for Le Système International de Unités. Okay, it's an international system of units. The SI unit of cycles per second is called the hertz. Which is abbreviated with a capital H, lowercase z. Also, it can be expressed as reciprocal seconds. S to the -1. Okay. So let's talk about this electromagnetic spectrum, the order of that electromagnetic radiation. So the order is, and you might find this easier to do like on your paper instead of being kind of portrait landscape. So you might choose to like turn your outline to the side and write this in the margin. Ideally, you'd like this to be all on one line. I don't know if I can do that. I'll try. Okay, I'm going to kind of turn so I can go from corner to corner. So I'm going to have my radio, my radar. So these are my forms of electromagnetic radiation. My microwaves. My infrared. My visible. My ultraviolet. My X-rays. And then my gamma rays. Now, all the visible spectrum includes all the different colors of light. So this visible spectrum, I can get more specific. This is going to be the Roy G. Biv that you've probably learned at some point in the past, right? So this is going to be red, orange, yellow, green, blue, indigo, which really is in a different color, and violet. Now, one way to kind of remember that, right? UV, that's ultraviolet, and here's my violet. Infrared, and here's my red. Okay? So, now, frequency and wavelength are inversely proportional. So, my frequency is increasing as I go from left to right here. So radio has the lowest frequency, gamma ray has the highest frequency. And this frequency is measured in seconds to the -1 or hertz. If my frequency is increasing that way, then my wavelength as I go this way is decreasing because they are inversely proportional. So my longest wavelength are radio waves. My shortest wavelength are gamma rays. And that has to do with why ultraviolet X-rays and gamma rays are more dangerous for you. And they do more damage to your cells. So this is that electromagnetic spectrum. And this is all of these different forms of electromagnetic radiation in order of increasing frequency and in order of decreasing wavelength. All right. What then? The last thing we want to talk about before we're done today is the speed of light, which is abbreviated with a lowercase c. The speed of light is the product, which means that it's going to be multiplication of frequency and wavelength. Remember, we saw this equation on our ChemQuest. Our equation for this is that C equals wavelength times frequency. Remember, when we manipulate this equation and we have wavelength on one side and frequency on the other, we get a fractional number, which tells us that this is inversely proportional. So wavelength and frequency are inversely proportional to each other, which means as one goes up, the other goes down, which is why here we had which is why we have frequency increasing here and wavelength decreasing, because they are inversely proportional. So that brings us to where we were going to stop for today. You do have some homework today. Your homework today is homework number 7. And it is on page 370, 7, 9, and 10 to answer those questions. Have a good day. Talk to you tomorrow.